Okay, I know this says section 5.5, but in our textbook it's not. And I know it doesn't say trapezoid rule, but it is. So what we're doing here is kind of like what we did with the left ram, LRAM and RRAM. And really, like we've talked about, it's only beneficial to use this process that I'm going to show you if you don't have the function, so that you can't find the antiderivative, or it could be that the function is too difficult to work with. So if you know the function and can find the antiderivative, then you're always better off using integrals to find the area. But sometimes it could be that the function is too complicated to find the antiderivative, and that can happen. Also, and even more importantly, if you don't have the function, but if you only have measurements, if you only have data, then this is what you're going to do, just like LRAM and RM. As a matter of fact, probably the trapezoid rule should have been taught at the same time, but it's not in our textbook, and I just kind of follow the order of our textbook. So this is just going to give us an efficient method, and it's better than LRAM and RRAM. So just as kind of an example to show you how it works, now obviously we would just do the antiderivative and use the fundamental theorem of calculus part 2 to find the area under the curve. So if you wanted to actually find that area, you would evaluate this integral. So when you do the antiderivative, and then you're going to substitute the limits in, for the 4 and the 0, plug them in and subtract. Remember, that's the fundamental theorem of calculus part 2. So we get 20/3 or 6.6 repeating, and that is the actual area under the curve of this function from 0 to 4. So remember, and I think this was the same example we used, the left-hand rectangular approximation means you're using the left endpoints to determine the height of the rectangle. And when you plug in those left endpoints, the 0, the 1, the 2, the 3, the 4, then you get these particular values here. And when you add up all the areas, you get 5.75. That's too low, which shouldn't surprise us, because notice that we have that the rectangles are all beneath the curve, and so we have this the white space there. So we know that the estimate's going to be too low. If you use the right-hand rectangular approximation method, remember, then you're using the right endpoint, so you're using the 1, 2, 3, and 4. So you would determine the heights of the rectangles, and this estimate is going to be too high. Now, if you average the two, then you do get 6.75, which is a better estimate, and we talked about that. It's not the same as the midpoint, but it is, it's a good estimate. You could do that. And when you do, it's still too high. Remember, 6 2/3 is what 6.66 repeating was what it actually was. So we can see this is a little too high. It actually is a 1.25% error, but it's too high. Averaging the right and left rectangles is actually equivalent to finding trapezoids. So if you were to find trapezoids, which of course means you've got your, think about how you find the area of a trapezoid. You add the two bases, you multiply by the height, and in this case the height would be the interval, the width of the rectangle, and then you divide by 2. So if you do that, okay, notice you're going to add, you have 1 plus 9/8, that's these two pieces here. And then they don't have the times 1, because obviously it's just 1. I multiply by 1 doesn't change the answer. And then the dividing by 2, they did a half instead. So you do that, and then you do the next trapezoid, and then the next one. So notice that the 9/8, this height right here, gets shared by 2 trapezoids. This one, the 3/2, gets shared by 2 trapezoids. And this, the 17/8, gets shared by 2 trapezoids. But the ends, the 1 and the 3, those don't get shared. So you'll see that they're only on there once. So you're going to notice that when we talk about the formula for trapezoids. So we get all those areas, and if you add up all the areas of those trapezoids, you will get 6.75, which is the same as you get when you average the left and the right rectangles. So this leads us to the trapezoid rule, and it looks like this. So you're taking, the h represents the width of your subinterval, so that's kind of like the width of your rectangle. This is the divide by 2 part. So remember how I said the endpoints only show up once, the heights of those two, but notice all the other shared sides, they show up twice. So that's where that times 2 comes from. So that is the trapezoid rule. We're going to do an example in a minute of how to use that. So it gives us a better approximation than either the left or the right rectangles. So if you compare this with the midpoint rule, remember the midpoint, instead of taking the 0 or the 1, you're going to use a half, and then you're going to use 1.5 and 2.5 and 3.5 to determine the height. So you'd be plugging those values in to determine the height of your rectangles, and those are shown there. So if you add up all those and you come up with your approximate area, you get 6.625. Remember what it really was, 6.6 repeating. So this is too low. It's a 0.625% error, but it is too low. So the midpoint rule gives us a closer approximation than the trapezoid rule, but it's in the opposite direction. Now, the trapezoid rule gives us a slightly higher answer. It's an error that's too high. The midpoint also gives us an error, and our approximation is too low. And notice that the trapezoid rule gives us an answer that has twice as much error as the midpoint rule, but in the opposite direction. So if we use a weighted average and we calculate this, we can show that we would get exactly what the answer is. That's the exact answer. I think we have some ooh, ah. Wait, wasn't there? Oh, wow, I knew there was one more. Okay, the weighted approximation gives us a closer approximation than the midpoint or the trapezoid rules. Now, I'm going to go through this next part really fast. I'm not going to go through every little detail. They go through, and you're welcome to go through it, how we are merging and we're combining 2 of the midpoints plus 1 trapezoid divided by 3, and working some magic here to come up with this formula. It's really not magic, it's algebra, but I'm not going through all the steps. But it leads us to something called Simpsons Rule. And one of the things I want you to notice is this time, h is the width of our subinterval. We're dividing by 3 this time, and that's because we're taking 2 midpoints plus a trapezoid, so there were 3 things. That's kind of, yeah, because we're taking an average. So we have the endpoints only show up once, but then here we have 4y1 plus 2y2 plus 4y3. We bounce back from the 4 and the 2 and the 4 and the 2. If you want to know where that comes from, you just have to go through the PowerPoint a little slower. In addition to this, in order to use Simpsons Rule, n has to be even. You have to have an even amount of sub-intervals. That was not true for the trapezoid rule, but it is in order to use Simpsons Rule. So using just, again, this function as an example, you can see that you would get, and this one actually turns out to be exactly the answer. Simpsons Rule does not always give exactly the answer, but when it's a parabola, it does. So Simpsons Rule can be, well, and that's what this was talking about here. That's why it came out exactly. And Simpsons Rule gives us a very good approximation with relatively few subintervals. And again, remember when we're going to use one of these. The Trapezoid Rule and the Simpson Rule, really we only want to use these when we don't know the actual function. Because if we know the function, we're going to do an integral and calculate the antiderivative and use the fundamental theorem of calculus part 2. But this is helpful when we have data, and that's what we're going to do an example of right now. All right, so here's a problem, stocking a fish pond. As the fish and game, this is number 10 from this section in your textbook. As the fish and game warden of your township, you are responsible for stocking the town pond with fish before the fishing season. The average depth of the pond is 20 feet, and that is going to be important for us. Grab this pen tool here. So the average depth of the pond is 20 feet. Using a scaled map, you measure distances across the pond at 200-foot intervals. Well, that seems important, as shown in the diagram. Use the trapezoid rule to estimate the volume of the pond. Well, we just got done talking about how the trapezoid rule helps us to find the area. So actually, using the trapezoid rule is going to give us this surface area of the pond. That's why this depth is important, because if we want to find the volume, we have to find the surface area of the pond times the average depth. So that's what we're looking for. So in part A, applying the trapezoid rule, we're going to, let's identify what everything is. So we've got h is our subinterval. So in this case, h is 200 feet, because that is the interval between these lengths that we've measured. So remember that the why not gets used once. Now in this case, interestingly enough, it's 0. So you can't ignore that. You can't use 520 as the first measurement because then you would not be counting this piece at all. Same thing would be true down here. So, so to find this is going to give us the area using the trapezoid rule. We're going to have 200 over 2. And then why not would be 0. So we need 0. We have a 0 plus 2 times 520 plus 2 times 800 plus ... because I don't want to do them all, 2 times 860 plus, and then the last one again would be the 0. Now that's not always the case. They're not always going to be zeros, but it was the case here. Okay? Okay, so I paused the video so you didn't know that though, so I could go through and make the calculation. Now what I just did is a shortcut, I just added the 520, 800, so I added all these. Hopefully I didn't push any wrong buttons on my calculator, didn't double check, and multiplied that sum by 2 since I was multiplying them all by 2, and then I got that answer and multiplied by 100. So I end up with 1318000. So we have 1,318,000, and let's think about the units. So here we have square feet. Okay, well, we want the volume, so that means we're going to have to take 20 feet times 1318000 square feet, and we end up with 26,360,000 cubic feet. And that's our volume of this pond using the trapezoid rule. Now, instead of going on to part B, we're actually going to redo the same problem. So I guess I'm going to call this part C. It's not really there. But let's see what we get if we do Simpsons Rule instead. Now, I can use Simpsons Rule because if you count the subintervals, now be careful when you count those, you count the intervals. So you can see 1, 2, 3, 4, 5, 6, 7, 8. I have 8 different segments. So n is even, and actually n is 8 in this problem. Our width of our subinterval is still 200, so h is still 200. You can't use these if you don't have equal intervals. So that's kind of key on that. If you were doing the trapezoid rule and you did not have equal intervals, you would have to just calculate the area of each trapezoid separately and then add them all together. All right, so using Simpsons Rule, we're going to get 200 over 3 times, and we're going to have a 0, plus 4 times 520, plus 2 times 800, plus 4 times 1,000, plus 2 times 1140. I'm going to kind of list these all out since they're changing. So where am I at? 4 times 1160 plus 2 times 1110 plus 4 times 860, which is good because I was supposed to have 4 before the last one, which is just 0. Okay. All right, so this 20,260 is what I got when I did this sum here. So I still have to take that and multiply by 200 over 3. So I'm going to multiply by 200 and divide by 3. And I get 1350666.6 repeating. So I could just kind of round that because this is an approximation, remember. Then we have to multiply that by 20 to get the volume. So we're going to take times 20. And we get 0, 1, 3, 3, 3, 3. I'm just going to leave it there since it's an approximation. I know it's like, wait, to the 3 decimal places, but on this one, I think we're good with this. So this is in cubic feet. Now, if I compare this answer, 27, roughly 27 million, to the other one we got, notice they're not that far off. Simpsons is going to be better, so this is going to be closer to the real answer. Now, going on to part B, you plan to start the season with 1 fish per 1,000 cubic feet. So I don't care which answer you use. You guys can all decide which one. You can either use the trapezoid or Simpsons, or you can do both and compare them. And think about, okay, here's my volume in the pond. I'm going to start with 1 fish per 1,000 cubic feet. So think of what you would do to do that part, because we're going to figure out how many fish we need. You intend to have at least 25% of the opening day's fish population left at the end of the season, so you can repopulate. What is the maximum number of licenses the town can sell if the average seasonal catch is 20 fish per license? So I'm just telling you, this is not calculus. This is just a little bit of basic math. So I'm leaving this part for you guys to do on your own and talk about that and come up with that. I've just kind of demonstrated how you could use the Trapezoid Rule or Simpsons Rule, and then you have a few homework problems that you will apply those rules to.